Hello, my name is Jesse Schottner, and I'm recording the video for part 1 of Project 4. I will be doing the Fluent 2D flow of air over a whole stationary cylinder at Inviscid, Laminar, and Turbulent flows. Someone else in my group, I'm working with Ethan Aldrich and Connor Freed. One of them will do the video for part 2. I will go through the entire part 1 from scratch. And as you can see here, I've already done each sim already, but again, we're going to start from scratch. So we're going to create a new fluid flow system, give the name it Inviscid Sim 2. And for geometry, I'm going to open Inventor. For every project, I've used Inventor to create the CAD because it's just easier for me to do it in here and it's quicker. We're going to go to New, we're going to go to Part, and we're going to go to Tools, and we're going to switch the units to meters because that is what the diameter should be in. We're going to click on Sketch. We're going to go here. We're going to do our center at the center of our circle in the middle, which will make our graphs easier to use. And then we will make a rectangle to encase it for the flow. I decided to do a rectangle of 25 over 25. This creates the blockage ratio that we discussed, which is 10% of the diameter. It's much lower than that, so this totally fits. And that should be good. So we're going to click Finish. And to make this a surface, we go to Sketch, we go to Patch, we click this, and there we go. As you can see, we have our surface now. We can check some measurements, 1 millimeter diameter, 25 and 25. We're going to go to Save As here. As you can see, I've already done the other one. We're going to just do 2.0, and we're going to save it as an Inventor file, and we're going to export it as a step file. There we go. Cool. We're going to exit that out. Back in Workbench, go to Geometry, import geometry, browse, and we're clicking part 2. And now we'll open the mesh and we'll do that. Alright, so our mesh has loaded now, and the first thing we're going to do with our mesh is insert method, select the surface geometry, and we're going to do triangles as our main method, not quadrilaterals. We're going to click Generate, and as you can see, we have our mesh that converges more towards the cylinder. However, this would be horrible, so we're going to refine it a little bit. First thing we're going to do is we're going to do a mesh sizing, and we're going to click the edge of our cylinder, and we're going to size this by further cells, and we're just going to do a simple number of divisions. We're going to do 1200. This is what I found to be the best, and we're going to do blend the neighbors, no, capture curvature, no, so it's and hard behavior. Before we do that, we're also going to go to mesh, and we're going to go to sizing. This to feature size, I don't know what the default is, but we're going to make this smaller because I found you get a tolerancing issue if you don't. So we're going to do 1e -0.05. Okay. Click Generate. And as you can see, we have now created much finer mesh as we get closer and closer based off of those number of divisions. But this still isn't what we want in terms of our statistics. We're still very low elements and nodes. So in order to fix this, we're going to add another mesh system. Oops, that was wrong. We're going to add a inflation, and that's going to go around the main cylinder. So we're going to click this geometry first, apply, and then we're going to click the edge as our boundary. We are going to click first layer thickness. For first layer height, we are to pick 2e -0.02. That is what I have found to be the best. Maximum layers, we're going to go to 300, which will basically expand our circle of cells around the cylinder. And growth growth rate, we're going to do 2.5. And we're going to click generate there, see what it gives us. Give it a second to load. Okay, so our mesh is done loading. And if we go to here, you can see we got this massive circle here. But these cells are also very big on the outside. So we're going to go back to sizing and, sorry, we're going to defaults, and we're going to switch our cell size from this, which is a very big cell size, and we're going to make it much smaller. And we're going to do 0.1 meters. Click generate again. This will probably take a minute. Okay, so our mesh is completely done, and as you can see, there's a lot of cells in our mesh. We have our massive round inflation around our circle to help with those closer laminar, turbulent, and inviscid flows, and made the rest of it fine to help as well. We're close to 500,000 elements, so we should get very good results. So we're going to close that mesh here and go back to our workbench. Okay, so our mesh is updated and ready to go. We're going to open Fluent at setup, double precision for processes. That is the max we can do for the student version. Take a second to let that load. Okay, so our setup has now opened, and the first flow we're going to do is the Inviscid. So we're going to go to our models, our viscous, select Inviscid. Materials, fluid. Our air is good to go. Density is fine. There is no viscosity in an inviscid flow. Cell, zone conditions, fluid, looks good. It's air. Boundary conditions. I realized I didn't name the mesh. I'm going to go back and name the stuff in the mesh. Okay, we're back in the mesh. I forgot to do this when I did the Sims originally as well. Anyway, this will be our inlet. We go to create name selection, inlet. This, shocker, will be our outlet. Top and bottom is just going to be symmetry. These aren't really walls. And finally, our cylinder, which will be cylinder wall. Name selections look good. Amazing. Click generate again just to make sure it works, and it does. Mesh looks good. We're going to exit out of there, and I will see you back where I left off in setup. Okay, so we're back in the setup, and our model is still Inviscid. Our air should still be 1.225. We're going to go to inlet, and the project tells us to put in an inlet of 5 meters per second for Inviscid. So that is what we're going to do. We're going to do velocity, magnitude, apply. Just in case, we're going to check everything else. Outlet should be good. Amazing. Cylinder wall. That's perfect. Symmetry, nothing. This should be nothing. Awesome. So we're going to close out all those, and we're going to go to reference values, and we're going to make sure it's all from the inlet. Very nice. Reference frames, that's good. Our methods are going to stay, we're going to change. We're going to go to simple for scheme, and pressure is presto. I found the best results from this. If you do the other ones, you get weird numbers. Doesn't work. So again, we're going to go back to reference frames. No, we're not. We're going to go to report definitions, and we're going to report the drag coefficient for the cylinder wall. Actually, hold on. Let me delete that really quick. We're going to re-add that because I want to do print to console, which means we'll print every time on every iteration. Splendid. Monitors, 1E -6 for every single one. Click OK. And great. That should be everything we need. We're going to initialize. Initialized went smoothly. And then we will run the calculations. Okay, we're going to go to run calculation, and we're going to do 1,000 iterations. It might converge, hopefully it does, but that will just give us a safe bet. And I will be back when this is done. And just to show that the sim is running. This is it at the beginning. Okay, so we're back and our Inviscid solution is done. As you can see, our CD is basically 0, and we can report that definition again here. And again, very, very, very close to 0. And the next thing for us to do is to show the CP distribution and the velocity distributions. So we're going to go to plot. We're going to go to XY plot. We're going to create CP distribution. Click cylinder wall, pressure coefficient, and we're going to click save and plot. And as you can see, it goes from 1 to -3, exactly how it's supposed to for an Inviscid 1. And that's wonderful. And we're going to create another plot here for velocity. This should go like, opposite shape is this here. And it does. It goes from 0 to 10. 10 makes sense at the top because your maximum velocity for Inviscid flow at the top of a cylinder is twice your free stream velocity. So that's what we got for those. And we're going to go into post for the contours. Okay, so our setup is updated. We're going to go to results and we're going to show the velocity and pressure contours. So to create this, we're going to go here, velocity contour. Excuse me. We're going to go to symmetry 1. Click on velocity, 110 contours, click apply. Cool. And as you can see, it's an even distribution as it should be. We're also going to click on velocity streamlines because it says to show the streamlines. And you know what? This will come in handy later. Don't worry about it. We're going to go back to, it didn't save. We're going to go to velocity stream again. Start from inlet, domains, 250, click apply. And if we shut off the velocity contour, you can see our streamline here looking pretty good, pretty even. Over the contour, you can kind of see it as well. And we're going to create our pressure contour. Looking good. Going to go to 110, close those. And this should be the exact opposite, and it is. Compared to our velocity, which is max at the top, pressure is minimum at the top. And it is an even distribution because it is Inviscid. There's no flow separation. There's no slip condition. It is just free velocity flowing throughout the entire thing. So that is everything for the Inviscid. We are going to do the laminar and turbulent next. So we're going to close out of our results here. And what we're going to do is we're going to create 2 Fluent flows. We're going to create one here and one here. You already saw me do the geometry and mesh. We're going to do the exact same thing for laminar and turbulent. It worked before. It should hopefully work again. So we're going to go to our setup and let that load. Double precision. Solver processes 4. Okay, so our ANSYS Fluent has opened. I realized I had it paused for a little bit, so I'm just going to go back and show. Viscous laminar, switch it to laminar model. Fluid, air, density stays the same. We're switching our viscosity to be very thick to 0.05. This is good for air. And our inlet, we're keeping it 5 meters per second. If you put these calculations for Reynolds number, you'll get a Reynolds number of around 122, which is very laminar. It's very low. And it should give us some vortex shedding in the wake. So we'll see when we run it. Everything else should be good to go. Cylinder wall should be nothing here. Awesome, because it's laminar, we now have these options. It's stationary wall and it's no slip. That is perfect. We're going to close that out, close that out, close that out. We're going to go to methods and we're going to do coupled, and pressure is back to presto. Again, these gave me the best values. Port definitions, you already know the drill. Drag, print to console, let's just name it, drag coefficient, and we are good to go for cylinder. Residuals, 1E -6. I could have copied the setup as well, but I didn't want to mess anything up with the data because it's just going to bring the same data over. And that should be good. We have all that good to go. We're going to, got to do reference values. This is an issue I came in before, is if you don't set these, you're not going to get the right stuff. Viscosity, velocity, and density are all set up, good to go. Amazing. We're going to go to initialization, click initialize, let that sit for a second. Okay, so the initialization is done. We're going to go to run calculation, and number of iterations, 1000. And we're going to click on calculate, and I'll be back in a second. Once again, I'll show the simulation is running, and I'll be back when it's done. Alright, so our data actually converged at around 620 iterations. Drag coefficient is very, very low. And we're going to reference that really quick. Or, sorry, I'm going to go to report definitions. Compute, 1.04. Very solid number for laminar. And now we're going to go to plots, just like we did before. And we're going to show our CP distribution first. Cylinder wall, looking pretty good for laminar. Should not start over 1, but the trend is very nice. And when you see the report, you will see the combination compared to the rest. Making another plot for velocity. This should be nice and flat. And it is. It's 0, right? No slip condition. Makes perfect sense. Once again, we're going to close out here. Sure you want to click yes. Click OK. And we're going to go into post to once again show the contours. We're back in the workbench. We're going to open up our results. And just like last time, same exact thing. Velocity, contour, symmetry 1, velocity 110. Now this one is going to look a lot different, and it's going to have a lot more movement to it. Beautiful. We have a massive wake region after the laminar, for the laminar flow, which makes perfect sense because you get more separation for that pressure gradient in the back. And we're going to look at the streamline as well. Velocity stream. Start from inlet, 250, apply. And you can't really see it over this, but as you can see, we got this. And there should be, so there isn't anything showing here, but there should be swirls here. In my other sim, there are swirls. It could just be it's more fine, but realistically there should be some swirling and some vortexes here. But this is the big wake region you would be seeing in this scenario, so it does make sense to a certain extent. And then we're going to look at the pressure. And if you look at the report, you'll see it looks more legit. Pressure contour, symmetry 1. Yep, apply. Actually, it works right over that velocity stream. This is good. Highest pressure at the front. Little bit low pressure in this wake region. As you can see, it kind of extends, but pretty standard for laminar. So we're going to exit out of that, and we're going to go to our final piece, which is the turbulent flow of the project. So we have our mesh here. We're already good to go. We're going to go to setup, and let's get this done. Okay, so we've opened the Fluent for the Turbulent, and let's get started. The model, we're going to switch it to Viscous Spillardo Almaris, whatever you pronounce it. That gave me the best results. Density stays the same. We're going to switch this to 0.00001. It's basically the same as what it was before, but just a little more precise. This Reynolds number, if calculated, will be around 700,000. It is massive. It is absolutely turbulent. And it should give us a narrower wake region at the end. So that's good to go. Cell zone condition, let's make sure this is what we want, and it is air. Boundary conditions, inlet, we're gonna switch this to 6, and once you calculate the Reynolds number with that, you'll get around that 735,000 to be exact. Everything else is good to go over there. We are going to go to our methods, and we're going to do coupled and second order. Keep it at that. That gave us the best results. Set reference values to the inlet, or everything will be screwed over. Density looks good, viscosity looks good, and velocity looks good. Excellent. Methods were good. Report definitions, you know the drill, force, drag coefficient for cylinder wall, okay. Wait. It's fine. It doesn't need to print out. We can just show it at the end. That's good to go. Monitors, residuals. Because it's turbulent, you add another residual here. But it's the same idea. We want it to converge very nicely. So reference values are good, residuals are good, drag's good. We can begin initialization. Okay, initialization is going to go into run calculation. We're once again doing 1,000 not 10,000. 1,000 iterations. And hopefully, like our laminar, it will converge. Okay, so 10,000 iterations, click calculate, and let's see what happens. Alright, and as you can see, our calculations are up and running. I'll be back when they're finished. Okay, so our calculation is complete. As you can see, our values converge pretty well. Our drag coefficient at a very solid number should be less than laminar, which is good. We're just going to go to report definitions and confirm that. As you can see, we got 0.46, which is very, 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 very nice for a turbulent value. Now we're going to go to our plots, and just like before, CP distribution. We're going to go to pressure coefficient, cylinder wall, save plot. That is absolutely beautiful. That is exactly how turbulent should look, trailing off at the end as the pressure recovers a bit. It's exactly how it should be. Make another plot. Velocity. And this should be exactly like, boom, 0. Exactly at the minimum. That's how it should be. It's no slip. Also, just for quick reference, every time I get this data, when I did it before, you would write the file here, name it whatever you want, and go from there. And for the final time, we'll exit out of Fluent, and we'll open the post CFD and show the contours. Alright, we're back in Workbench once again. Gonna click on Edit and open up results. Ignore these errors. These errors do not matter. Once again, we're going to look at the velocity and pressure contours. We've looked at the distributions for this and the coefficients. So let's get started. Velocity contour. 110. There we go. As you can see, a much smaller wake region, which makes perfect sense in the terms of turbulent as the pressure recovers and we experience less drag. We go to our streamlines. Can't really see that, but you can here. Once again, much smaller. Again, there should be some wake little vortexes forming here, but the mesh was very fine in this case. You will see that in the report. And finally, our pressure contour, which for the most part should look similar to what we got last time for laminar. As you can see, stagnation at the front is the same. Pressure at the back is much higher as the pressure recovers, disclosing that wake region. with that, that is all for part 1. We went through the contours for velocity and pressure for every single case, along with the streamlines, velocity and CP distribution for each one. That data will be exported to Excel. You will see it in the report. The drag coefficients as well, and we've discussed a little how it's supposed to look compared to other things. You will also see that in the report. Someone else will do part 2. Thank you very much for watching. Have a great day. Bye.